Hello everyone. Today I shall discuss mechanical properties of fluids, chapter 9, class 11, physics. So today we are going to discuss about mechanical properties of fluids. So what is given in mechanical properties of fluids? See here. First of all, we want to know the definition. What are fluids? Actually, substances that can flow, that is liquids and gases, these are known as fluids. They do not have a definite shape of their own. What are the key differences? Liquids, nearly incompressible, have a fixed volume, and in gases, highly compressible, fill the entire volume of the container. That's the difference between the liquids and gases. Now we are going to define what is pressure. What is the definition? The normal force if exerted by a fluid per unit area, that is the pressure. Actually, pressure is a scalar quantity, it has no direction. Therefore, you can say that pressure equal to force by area. Units. SI unit is Newton per meter square, or you can say it as Pascal. Common unit, atmosphere or ATM. And we should know that 1 ATM equal to 1.013 into 10 to the power 5 Pascal. This is the standard pressure. And you see, if this is the area, the normal force means perpendicular to the area. Perpendicular means what? It is 90 degree to the area. That is known as normal force perpendicular to area. So the normal force exerted by a fluid per unit area is the pressure, right? Now we are going to discuss with another important thing, that is this one. What is this? Density. So you have to know the definition of density also. What is that density? That is mass m per unit volume v of a substance, or rho equal to m by v, that is mass by mass by volume. What is relative density? It is the ratio of the density of a substance to the density of water at 4 degrees centigrade. It has no unit. Since it is relative, it has no unit. It is just a number. Now we will find the pressure difference between pressure variation with depth. We see that pressure inside a fluid increases as we go deeper. Now derivation sketch. Imagine a cylinder of fluid with height h and a base area. Suppose this is a base area and this height is h and base area is this one, a. So what we got? Forces acting on it are downward force from fluid above, that is P1 into A, right? P1 into A. Weight of the fluid of cylinder, weight of the fluid cylinder, m into g, mass equal to m into a into h, that is rho into volume, because mass is rho into volume, rho is this one and volume is a into h, m is area into h. So mg, a rho h into g. And upward force from fluid below, that is this is the upward force, that is P2 into A. This is the upward force P2 A. This is the upward force. So what we get in equilibrium? The upward force is equal to the downward forces, right? So you can write P2A is equal to P1A plus rho A Hg. And here you can find that the area will be that the area will be cancelled. This area. Therefore, P2 minus P1 will rho GH. Therefore, P at a certain depth, will be P at the surface plus rho GH. This is the formula for pressure variation with depth. So the formula is, what is that? P depth equal to P surface plus rho GH. This is the formula, right? Now, if you want to know more things, let us find the next thing. Next one is this one. What is that? Now we are going to find atmospheric and gauge pressure. What is that atmospheric pressure? Actually, atmospheric pressure, this one, atmospheric pressure or defined that atmospheric and gauge pressure. Atmospheric pressure, pressure exerted by the Earth's atmosphere at sea level. What is the pressure? Pressure at atmospheric pressure is 1.013 into 10 to the power 5 Pascal. Right? That is the atmospheric pressure. Now we can see here that this is known as atmospheric pressure. Absolute pressure, the total or actual pressure at a point, that is P equal to PA plus rho G. P is the atmospheric pressure plus rho G. This is the actual pressure. And gauge pressure, the difference between the absolute pressure and atmospheric pressure is the gauge pressure. This is what most pressure gauges measure. That is PG, gauge pressure equal to P minus PA, and that is equal to rho G H. This we measure generally rho G H. That is the gauge pressure. Is P minus PA, that is atmospheric pressure. So we are getting rho G H. So next one is hydrostatic paradox. What is that hydrostatic paradox? You find that pressure at a certain depth in a liquid depends only on the depth and not on the shape of the container. This is why the liquid level is connected. This is why the liquid level is connected. This is why the liquid level, the pressure at a certain depth in a liquid depends only on the depth and not on the shape of the container. This is why the liquid level is connected in connected vessels or different shapes is the same. This is hydrogen. Suppose this one connected with the liquid, you can see here that the level of the liquid will be same at all the points, but this is something wrong. It will be up to here because this is connected with each other. This is wrong. This liquid is up to here, and the level of all the liquids should be same, right? This is the level. This is wrong actually. The liquid will be up to here. This is known as hydrostatic paradox. The pressure at a certain depth in the liquid depends only on the depth and not on the shape of the container. This is why the liquid level is connected in connected vessels of different shapes is the same. That is hydrostatic paradox. Next important thing is Pascal's law. Statement: whenever external pressure is applied on any part of a fluid contained in a vessel, it is transmitted undiminished and equally in all directions. That is Pascal's law. Application: the hydraulic lift. Based on Pascal's law, it uses fluid to transmit pressure. A small force F1 applied to a small piston A1, area A1, this is the force, this is the area A1, and creates a pressure P F1 by A1. The base pressure acts on a larger piston A2, producing a large upward force F2. And you see, since according to Pascal's law, pressure P1 equal to P2. Therefore, F1 by A1 equal to F2 by A2. Or you can find F2 equal to A2 by A1 into F1. So what we get, the factor A2 by A1 is called the mechanical advantage. The factor A2 by A1 is called the mechanical advantage. IMP, this principle is the basis for hydraulic brakes, car lifts and hydraulic presses. So these are the important things you should know. These are the applications of Pascal's law, that is hydraulic brakes, car lifts and hydraulic pressure. And also it is used in cranes also. Right? So these are the various important things to know about this. And the next important thing is this one, that is solve numerical examples. So let us find how to find this. At a depth of 1000 meter in the ocean, find A, the absolute pressure. Find B, the gauge pressure. Find C, the force on the 20 centimeter in 20 centimeter window of a submarine. Density of seawater is 1.03 into 3 kg per meter cube and G is 10 meter per second square. So what is given? Height is given 1000 meter. Area is given 20 into 20, that is 0.24 meter square, we change into meter square, and P 1.03 into 10 power 3 kg per meter cube. PA it is 1.0 into 5 Pascal, it is atmospheric pressure. So formula used, gauge pressure is rho G H, you know this one. Gauge pressure is rho gh, right? And absolute pressure P equal to Pa plus Pg, right? And F equal to Pg into gauge pressure into area. That is the so gauge pressure equal to Pg, that is rho gh, rho into G into H, right? That we are getting the rho density of water here 1.013, 1.03 10 to the 3 into G is 10 and H is 1000 meter. So 103 into 10 to the 5 Pascal, nearly 103 atm. Absolute pressure is P equal to Pa plus Pg. Pa is how much? Pa is this one 1.01 into 10 to the 5 plus Pg, this one, that is 103 into 10 to the 5, therefore 104.0 into 10 to the power 5 Pascal. This is the absolute pressure. And force on window. So you got the net force is due to the gauge pressure, and the gauge pressure is F. F equal to Pg into area, right? Therefore Pg is how much? This is the Pg 103 into the 5 Pascal into 0.04 meter square. So we are getting 4.12 into 10 to the power 5 Pascal. In this way we can solve any problem, right? So the next important thing is that of this one, fluids in motion or hydrodynamics. That is types of fluid flow. So streamlined and steady flow. Velocity of fluid particles at any point remains constant over time. The paths of particles, streamlines are smooth and do not cross with each other. Turbulent flow, irregular, chaotic flow that occurs at high speeds or when there are obstacles. Equation of continuity, this is very much important. This is a statement of the conservation of mass for an incompressible fluid. The product of the cross-sectional area A and the fluid's velocity is constant at all points along a pipe. A1 V1 equal to A2 V2 or AV equal to constant. This is the equation of continuity. Where the pipe gets narrower, the fluid speed increases, right? This is what is called the equation of continuity. Now we are going to explain about what is Bernoulli's principle. A statement. For the streamlined flow of an ideal fluid, incompressible and non-viscous, remember that it is applicable for incompressible and non-viscous liquid. The sum of the pressure energy, the kinetic energy and potential energy per unit volume remains constant. So this principle is based on the law of conservation of energy, right? And what is that? P plus half rho V square plus rho GH is equal to constant. Breakdown of terms, P is equal to pressure energy and half rho V square is equal to kinetic energy and rho GH is the potential energy. That is pressure energy, kinetic energy plus potential energy equal to constant, and that is known as Bernoulli's principle, right? Now we learn other important things. The next one that we are going to deal with is this one, that applications of Bernoulli's principle. What is that application? Now we'll find now a speed of efflux or Torricelli's law. Describes the speed of a fluid flowing out of a small hole orifice in an open tank, a height h below the surface. The speed of efflux is the same as the speed of a body would gain by falling freely from height h. That is, if a body falls from here, the speed at this point will be same as the speed of efflux. And the speed of efflux is equal to root 2 g into h. This is the speed or velocity of this water at this point, right? This is the speed of efflux, or you can say is a Torricelli's law. And the dynamic lift on an aerofoil airplane wing. The curved top surface of wing forces air to travel faster than the air below it. You see there is a curve here. So the particle, so the air moves in the curved particle, and here these are going straight forward, so it travels less distance. So and they reach this point at the same instant of time. So the speed at this upper end will be more than the speed here. So when the speed is more, pressure will be low. So this is high pressure and this is low pressure. Creates a zone of high pressure and low pressure. So we know that the pressure moves from high pressure to low pressure. That means it will be lifted upward. That is according to The curved top surface of wing forces air to travel faster than the air below it. According to Bernoulli's principle, higher speed means lower. You have to remember that higher speed means lower pressure. The pressure difference P bottom is greater than P top. So it creates a net upward force called dynamic lift and it was lifted up. So this is the principle or applications of Bernoulli's principle. The speed of efflux, Torricelli's law, and dynamic lift. Besides that, there are other things also that you want to know, that is the real world of fluids, and that is known about viscosity. What is viscosity? And it is defined by eta. Definition: the property of a fluid by which it opposes the relative motion between its different layers. It is essentially internal friction for fluids. Example: honey is much more viscous than water. Coefficient of viscosity defined as the ratio of shearing stress to the strain rate. That is F equal to eta A V by L. That F is the tangential force, A is the area of the layers, and V by is the velocity gradient. Is a unit. Newton second per meter square or Pascal second, also known as Poiseuille. This is the unit of viscosity. You can see here how you define the viscosity, the property of a fluid by which it opposes the relative motion between its different layers, is essentially internal friction of fluids. Honey is much more viscous than water. Coefficient viscosity at eta defined as the ratio of shearing stress to the strain rate. So in this way you can find the definition of viscosity, right? So here you see this is the definition of viscosity, and here you see this is a fixed plate, V is equal to 0, right? This is the moving plate, and you can see this is the velocity. In this way you can define the viscosity. Now the next one, what we want to learn, it is Stokes law. This is very much important, and terminal velocity. What is the terminal velocity? Stokes law describes the viscous drag force F on a small spherical object moving through a viscous fluid. F equal to 6 pi eta RV. What is eta? Coefficient of viscosity. What is R? Radius of the sphere. What is V? Velocity of the sphere. Now, if we want to find the terminal velocity, so the constant maximum velocity reached by an object as it falls through a fluid, it occurs when the downward force of gravity is balanced by the upward forces of buoyancy and viscous drag. Now, this is buoyant force and this is viscous drag, and this is weight, both are equal. At terminal velocity, net force equal to 0, so acceleration equal to 0. Equilibrium condition, weight is equal to buoyant force plus viscous drag. There are two forces, one is buoyant force, another is viscous drag. So this is equal to the weight, and by this we find a relation, that is Vt is equal to 2r square rho minus sigma into g by 9 eta, where rho is the density of the object and sigma is the density of the fluid. So terminal velocity is directly proportional to the square of the radius. You can find that terminal velocity Vt is directly proportional to the square of the radius. This is very much important in case of terminal velocity, right? Now we learn other important things, that is this one. We are going to solve a numerical examples on viscosity. How we are solving? You see this problem. The terminal velocity of a copper ball of radius 2 mm falling through a tank of oil is 6.5 cm per second. Compute the viscosity of the oil. Density of the oil is 1.5 into 10 to the 3 kg per meter cube, and density of copper 8.9 into 10 to the 3 kg per meter cube. So Vt, terminal velocity, is given, right? So it is given as 6.5 centimeter per second or 0.065 meter per second. We have to change into SI unit. This is radius is 2 millimeter, change into meter, 2 into 10 minus 3 meter. Rho, density of copper is 8.9 into 10 to the 3 kg per meter cube, that is copper, and sigma is 1.5 into 10 to the 3 kg per meter cube, that is oil, and G is 9.8 meter per second. Then the formula is eta 2r square sigma minus rho minus sigma g by 9 into Vt. So we put the substitute the values into the formula, and getting a result, eta is equal to 0.99 kg per meter per second or 0.99 Pascal second. In this way, if you find the different numerical problems of viscosity, right? So the next important thing is about surface tension. So we are going to learn what is that surface tension, how it can be defined. Surface tension concept: molecules on the surface of a liquid have extra energy compared to molecules in the interior. This is because surface molecules are pulled inwards by cohesive forces from the molecules below and not above the surface. The net inward force causes the liquid to minimize its surface area. The liquid surface behaves like a stretched elastic membrane. Surface energy: the excess potential energy per unit area of the liquid surface. The excess potential energy per unit area of the liquid surface, that is surface energy. Now, in examples of surface tension, raindrops are spherical due to surface tension. Insects walk on water due to surface tension. A paintbrush tip forms when pulled out of water. That is the examples of surface tension. Besides that, you can find that this is a molecule A, molecule B, this is molecule A. The molecule A, you see, this is the balanced force. But here in the surface, this is molecule B, right? There is a net inward force, So this inward force tries to minimize the surface area, right? So the surface area, right? So in this way, you can define this as net inward force and define the surface tension. What we find that molecules on the surface of a liquid have extra energy compared to molecules in the interior. This is because surface molecules are pulled inwards by cohesive forces on the molecules below but not from above. The net inward force causes the liquid to minimize its surface area. The liquid surface behaves like a stretched elastic membrane. Surface energy: the excess potential energy per unit area of the liquid surface. And the next important thing is now the summaries. What is that? Chapter summary: key concepts we have: fluids at rest or hydrostatics. Pressure: force per unit area increases with depth, P equal to PA plus rho GH. Pascal's law: pressure applied to an enclosed fluid is transmitted equally everywhere, used in hydraulic lift. Fluids in motion, hydrodynamics. Equation of continuity: mass is conserved where mass area is small, speed is high, that is A1 V1 equal to A2 V2. That Bernoulli's principle: energy is conserved, right, where speed is high, pressure is low. P plus half rho V square plus rho GH equal to constant. Real fluid properties. Viscosity: internal friction in a fluid resisting flow. Stokes' law: drag force on a sphere in a viscous fluid is 6 F equal to 6 pi eta RV, which leads to terminal velocity. Surface tension: due to cohesive forces, liquid surface tends to shrink and have surface energy. That is surface tension. Due to cohesive forces, liquid surfaces tend to shrink and have surface energy. And the last of this is the formula sheet. This is very much important for exam essentials. Pressure and depth. Pressure equal to force by area. Gauge pressure equal to rho GH. And absolute pressure is PA plus rho GH. This is absolute pressure. And what is Pascal's law? F1 by A1 equal to F2 by A2. And we can find as F2 is equal to A2 by A1. A2 by A1 into F1. And what is that F2 by A1? This is the mechanical advantage of the device. This is known as mechanical advantage. Mechanical advantage of the device. Mechanical advantage of the device. And fluid flow: AV equal to constant, that is continuity. P plus half rho V square plus rho G equal to constant. This is Bernoulli's equation. Torricelli's law: V equal to root 2 G. Viscosity and drag: Stokes' law: F equal to 6 pi eta RV. Terminal velocity, that is 2 R square rho minus sigma into G by 9 theta. Thank you everybody for watching this video.